Good morning, guys. It's Monday, October 5th. We are discussing enzymes, chapter 6. I hope you had a good weekend. Can you all hear me well?
Yes.
Good, thank you. So hopefully you started reading the text. I opened the sapling homework. So there are some math problems there as well. But this chapter, as I mentioned to you, has the most math problems of all the chapters in the textbook because it has to do with enzyme kinetics. And as we will learn, kinetics is a great way to learn about enzyme mechanisms. So kinetic studies are very important to enzymes. So I left quite a few math problems on the in the sapling homework. All right. So let's go to share screen. Let's go to share screen. And we stopped at discussing this slide on Friday. So we talked about why biocatalysis is so much superior over inorganic catalysis. Also keep in mind that these are not totally different types of catalysis because many enzymes utilize utilize metals as their cofactors. Remember cofactors, right? Cofactors are usually metals, which are not part of the amino acids, but enzymes can incorporate metals in at their active site. And we saw iron already, right? We saw iron, which is incorporated into the heme of a transport protein, hemoglobin. So, but enzymes utilize metals quite broadly. And remember from organic chemistry, from OChem 1, OChem 2, we use a lot of metals to perform organic transformations, right? So even such simple reaction as hydrogenation, we used palladium or nickel catalyst. All right, so that, and in addition, so obviously specificity, right? So we talked about specificity, we talked about lock and key. We talked about how large enzymes can differentiate easily between different substrates. Remember, substrate is a molecule that undergoes the chemical transformation. So the second bullet point here is the milder reaction conditions, right? So remember that in cells, pH is 7 in most cases. And so the reactions have to occur at pH 7. And in most cases at not at the body temperature of 37 degrees Celsius, right? So with organic reactions, usually remember quite a bit of heating is required, right? And here the enzymes have to be able to run these reactions at body temperature, with the exception of some thermophilic organisms, right? So there are reactions which are performed by enzymes of thermophilic organisms where the reactions can be done at 100 degrees Celsius and even higher. So this is a totally different area of biochemistry. And so when I say it's a totally different area of biochemistry, what I probably mean is just think about thermophilic organisms, let's say more than 100 degrees Celsius. What will happen to protein at 100 degrees Celsius?
Denature.
They will denature. So right. So these thermophilic organisms, they have come up with ways for their proteins to maintain their tertiary structure even at these high temperatures. And so it requires a total different set of communications between amino acids. It's the same amino acids though, same amino acids. It's just, you can imagine there are probably going to be many more disulfide linkages, many more sulfur in their structures, and many more covalent bonds, right? All right, then higher reaction rates. All right, can you imagine that now when we run an organic reaction or inorganic reaction, you know, you set up a reaction in a flask and then it takes hours, sometimes days. You can't afford that in a biological system, right? In a biological system, reaction has to occur within seconds, maybe even milliseconds, or even faster, right? So large enzymes can accomplish that. Capacity for regulation, another major important one, right? So just remember from OCHEM 1 again, when you have a recall one of the most challenging transformation we had in the OCHEM 1 was the hydrogenation of an alkyne, right? Hydrogenation of an alkyne to an alkane, which proceeds through an alkene, like that, right? So another molecule of H2. I mean, ideally, what we would want in such a reaction, let's say if this is the desired product, right? If this is a desired product, you want the reaction to stop here. So you want to be able to regulate your catalyst. So the catalyst performs the first hydrogenation, but stops and doesn't perform the second hydrogenation. So, and this is something that is not easy to accomplish without an enzyme. Needs regulation. So there are some ways for this reaction to be to make it successful, more or less. You guys remember the catalyst we used in OCHEM 1?
Lindlar's?
Which one?
Lindlar's catalyst?
Lindlar's, that's right. Lindlar's catalyst, we use that in OCHEM 1. It works, but it's very tricky. So in you know, obviously in lecture and on exam, we would just say Lindlar catalyst. Oh well, you know, from triple to double bond works very well. But if you actually go to the lab and you have to run a Lindlar reaction, hydrogenation, you will find that you'll probably spend weeks optimizing your reaction. It's still not very easy. And so with the enzymes, there's capacity for regulation. And obviously one can imagine, for example, let's say, how would you, if you were to design an enzyme, let's say you have all the amino acids, you can put them together into an enzyme. Like, how would you regulate this reaction? Let's say your catalyst is the enzyme, right? Like, what would you do to make this reaction stop at this point?
Binding site specificity.
Binding site specificity. Well, this alkyne, right? It binds to the active site. The reaction occurs. So what do you suggest? What do you suggest happens next?
So make that not be able to bind to the active site.
So you suggest that this will, well, this already is bound to the active site. The alkene, the product, it's still at the active site.
Can you modify the molecule somehow so it can't continue going forward?
Well, you're not so, well, then you kind of, if you modify the molecule, then you limit yourself pretty much as far as what you can do, as far as what kind of substrates you can use, right?
Can you add an allosteric inhibitor?
How about allosteric inhibitor? So which allosteric inhibitor could you add?
I don't know, just something that'll kick it out of the active site and then not let it go back in.
Okay, can you just look into the screen, come up with an allosteric inhibitor. It's right there, staring straight at you. This alkene. So this will be the feed. It's called feedback inhibition. So when as the alkene is produced, more and more of it is accumulated, right? And then more and more of it will bind to what you just said, the allosteric site. And this allosteric site will change the conformation of the enzyme in such a way that this second reaction will stop. Either, as you said, through maybe the product will leave the active site, or maybe there will be inhibition of the hydrogenation of the alkene. But the point is, yes, so as this intermediate product is accumulating, right, you can make it go back and bind to an allosteric site and stop the reaction from completing the second step. So the enzymes can do that, right? So in organic chemistry, we could not do that because the catalysts we used did not have the capacity for regulation. All right, and you can see that so the enzymes are highly specific, right? What does it mean? So here's one of the biosynthetic intermediates, charismic acid, and charismic acid can undergo variety of transformations. It can give you this hydroxybenzoic acid, aminobenzoic acid, this kind of acid. And one of the products is through this, what's known as a sigmatropic rearrangement, gives you this product. And if you put the enzyme, if there is no enzyme, it produces mixtures of products. But if you put the enzyme in there, it's highly specific. It will catalyze one particular reaction, and this will be your only product in the reaction mixture, right? So it's a great way to, so the enzymes is a great way to sort of to channel the biosynthetic transformations in one particular pathway and stop all the other ones. All right, any questions? So hopefully I convinced you that why the enzymes have to be so large, right? Why do we have enzymes with thousands of amino acids in them? Another quick slide. So we talked about enantiomers. Remember from OChem1, enantiomers. So here we have amino acid phenylalanine, right? So this is L-phenylalanine shown here. And this undergoes biosynthetic hydroxylation, right? L-phenylalanine undergoes hydroxylation at this position to give us hydroxy phenyl. Now, if you have D-phenylalanine, right? So basically this is the enantiomer. So these are enantiomers. Enantiomers. So the enzyme, which is composed of only L amino acids, it will differentiate between the two. It will use L-phenylalanine as a substrate to hydroxylate it, but D-phenylalanine will not even bind to the enzyme, right? Because the enzyme is, again, it's one mirror image. And remember, if the enzyme is all one enantiomer, then binding of these two will generate diastereomers, right? So think of the enzyme. Let's say if the enzyme is all L, right? And this is L-phenylalanine, LL. Now, if this is D, the enzyme is still L, but this is D-phenylalanine. So remember the mirror image of LL would be DD, but this is LD. So this is these are diastereomers, and diastereomers have different energies, which would result in the binding of this and no binding for that. And this, for example, this binds, oh, very well, this binds, but there's no reaction. So with enzymes, binding is not the end of the story. Binding is good, but the second step the reaction has to occur as well. Okay, so most enzymes will look like this, right? So they will, remember, the reaction will occur at the active site. Yeah, so this, with other proteins, we talked about binding site. With enzyme, we change binding site to active site. Active site, which serves as a binding site as well. It's just a more general term which describes that at this active site, not only it is the binding that takes place, but also the reaction. And so in most cases, this will be the key amino acids which will participate both in binding and the reaction. And one key thing, which I'm sure will be on the test. So the enzymes, remember, catalysts do not affect the equilibrium. You remember that from general chemistry, right? Catalysts do not change the position of the equilibrium, but they will only expedite the reactions. And so they will increase the reaction rates, and the reaction rate is given by this expression. So we have the Boltzmann constant, Planck constant, temperature. Obviously, the reaction rate increases as you increase the temperature, makes sense. And this is the negative delta G, right? So the more the, so this is the delta G of the transition state. Remember this? This is the sign for the transition state. It's not the overall heat of the reaction. It's the delta G of the transition state. We're going to look at the graph in just a moment. But keep in mind that this sign, whenever you see it, it means transition state. Okay, let's look at the next slide. I'll come back to this one in a moment. So here, here we have the ground state. Our substrate, S stands for the substrate. The substrate has to climb all the way up there, overcome some kind of transition state, and then drop all the way down to form the product, right? So delta G, this delta G is the heat of the reaction, right? Basically, after the reaction has finished, this is how much heat will be generated. But it doesn't tell us anything about the energy of the transition state. Remember I told you about table sugar, right? Even though when it burns, it produces lots of heat, but unless you actually somehow make it overcome this barrier, this transition state barrier, then nothing will happen to the table sugar. So you need to overcome, you need to give it enough energy or use a catalyst to climb all the way there and overcome this transition state. And how do enzymes do that? So in general, so if this is again, the black one is the uncatalyzed reaction that we just looked at, right? So the blue one is the actual catalyzed reaction. So you can see that catalyzed reactions actually generate a whole bunch of humps like this. If the actual reaction is just one hump, the catalyzed reaction is usually, especially with enzymes, in most cases, you will see 3 humps. And so how does this work? So let me write this out. We will see this when we talk about enzyme kinetics, but it's kind of the general expression for all enzymatic reactions. So this is the enzyme, this is the substrate. They come together and generate the enzyme substrate complex, right? It's right there. So there is some kind of transition state associated with that, but obviously it's much smaller, right? Because we're not performing any kind of chemical reaction. It's a small transition state compared with the uncatalyzed reaction. Then, once the substrate has bound, the reaction is occurring. The reaction is occurring at the active site. And the S is changing into the product. P is the product. And once that has occurred, so you can see that's the second hump, right? The second hump, and that's the transition state associated with the reaction. And the third hump is the actual departure of the product from the active site to basically vacate the active site for the next molecule of substrate to come in. And so you may ask, how do enzymes accelerate these reactions? Well, first of all, so when the enzyme binds to substrate, the net energy here is about 0, but there is some kind of activation energy here. So if there is an attractive force, right? So if you think about, so the enzyme has amino acids, substrate has functional groups which are capable of interacting with amino acids. Why is there an activation energy? So why can't just substrate totally, with huge amount of attraction, love, will just stick itself to the enzyme without any kind of activation energy, if all there is just attractive energy? What is so what favors the formation of this enzyme substrate complex is the attractive interactions between amino acids and the enzyme at the active site, right? And the various functional groups on the substrate. What is disfavored? So why would this enzyme substrate complex be disfavored as well? What is the negative for the formation of enzyme substrate complex?
Entropy.
Entropy, perfect. So so there's entropy. So it's enthalpy versus entropy. Remember, it's always enthalpy versus entropy. Always remember this Gibbs equation, right? Delta H minus T delta S. Always keep this in mind. It's always enthalpy versus entropy, right? And this is negative, this is positive. And we want this delta H to be negative, so the delta G can be negative, and we want this to be positive so that this minus can be bigger. So this also tells us why the enzymatic reactions are accelerated. So once this has bound, now you have enzyme substrate complex, the reaction actually is pretty fast. Now, if you think about it, in solution, let's say the reaction is not catalyzed, this black curve here, right? So the main factor which slows down this reaction and makes this transition state so high in energy is also entropy, right? So here you have the two substrates, or the substrate itself. Well, let's say it's a bimolecular reaction. You have two molecules of substrates, have so much freedom walking around, and here they have to find each other, stick to each other, and perform a reaction. Huge drop in entropy. And the enzyme already accomplishes this for you, right? So the substrate is already captured. It's already captured. And then all that needs to be done is for the substrate, it's frozen, it's rigid, it's already lost all its entropy. And it's basically a very simple transformation of substrate to the product. And that's why this hump is very small. And then the release of the product. Okay. Any questions about this graph? So this is how the enzymes accomplish their catalysis. 3 steps: complex formation, reaction, product dissociation. So keep that in mind. And again, the entropy is the bad guy, but it's overcome by the enzyme substrate attractive interactions. Enthalpy versus entropy. So enthalpy is attractive interactions, entropy is the disorder. And disorder always works against us because reactions are highly organized, which results in a negative entropy. All right. So this is some of the summary of what we just talked about, right? So what do enzymes do? They organize reactive groups into close proximity and proper orientation. That's what? That's the loss of entropy, right? But the enzymes can accomplish this for us, and they can compensate for this loss of entropy. Now, for the uncatalyzed bimolecular reactions, you have two free reactants, single restricted transition state, entropically unfavorable. Now, for unimolecular reactions, which is what we just looked at, it's still loss in entropy. Even though we're not talking about the two substrates finding each other in solution, you still have a flexible reactant. Imagine there's so much rotation about single carbon single bonds, right? So lots of degrees of freedom for the reactant. And for the reaction to undergo, for the reaction to happen, all that has to freeze. But if the enzyme can accomplish this for you, it can basically lead to this rigid transition state and can basically turn this entropically unfavorable in interaction and compensate that with attractive interactions with the active site. Then you can freeze and you can rigidify the substrate, right? And the reaction can occur. Okay, fairly rigid enzyme substrate complex. And the entropy cost is paid during binding. All right, any questions? So this is how the enzymes work. This is how they accomplish chemical transformations, right? Basically, they overcome the negative entropy at the expense of positive enthalpy, at the expense of attractive interactions. Okay, so here's some chemical experiments. Now, keep in mind, guys, that whatever happens with enzymes is just basic chemistry. In most cases, organic chemistry, because enzymes are organic molecules, right? So whatever works with enzymes has to work with simple chemical model systems. And there's, for each enzyme, people work on developing model systems to show that the basic chemistry works. If basic chemistry works, then you can say that yes, the enzymatic reaction, the mechanism that I'm proposing, is supported by a basic chemical model, right? Because if chemically it's impossible, then the enzymes are not magicians. The enzymes are not something that out of beyond reality, right? The enzymes work based on the basis of simple chemical principles that we learn in OChem 1, OChem 2. So these principles have to work in simple chemical model systems. So here's one reaction we're going to look at. So for example, the formation of this anhydride, right? So this is acetic anhydride, if you remember that, right? So this reaction, so we react with, so this is an ester reacting with a carboxylate, so acetate, in the presence of a base, right? So this is going to attack here, and this is going to leave, and going to form an anhydride. So let's give this a relative reaction rate as 1, okay? It's going to be a relative rate. We'll give it rate 1. Now, if you did not have any issues with entropy, so in other words, again, these two molecules have to find each other in solution. And so the reaction rate is slow because of the negative entropy, right? These two molecules have to find each other in solution, reduce degrees of freedom. But if you connect them already, pre-organize them like this, pre-organize them and connect them into to create one molecule, then under exactly the same set of conditions, right, you also form the anhydride, but you can see the reaction is what 100,000 times faster. And why is it faster? Because of the entropy, right? We don't have to lose so much entropy to pre-organize these two substrates and bring them into close proximity. They're already in close proximity. But how can we improve on entropy even more? Just look at this. What do these arrows mean? They mean something negative. They slow down the reaction. How do they slow down the reaction? Think of entropy.
Would it be because the molecule is folding onto itself?
The molecule is doing what?
Folding onto itself, kind of like becoming a more structured a molecule?
Well, the molecule is doing something. So how is that negatively affecting the rate of the reaction? So in other words,
It's undergoing, is it undergoing a cyclization, so it increases entropy?
so does it increase the so in other words, is the entropy favorable in this reaction or unfavorable?
Unfavorable?
Unfavorable. So in the transition state, again, this oxygen O minus has to attack this carbonyl and this has to leave, right? So in the transition state of this reaction, this bond is partially formed, this bond is partially broken. And so what happens to all these rotations? They stop, no rotations, right? In the ground state, when the reaction is not occurring, there's lots of freedom. Again, lots of degrees of freedom. There's lots of carbon-carbon bond rotations. The molecule is enjoying high entropy. Now, as you rigidify this molecule and prepare this molecule for the reaction, what happens to all these bonds? You freeze them. You freeze them, you lose entropy. You lose entropy, you raise the activation energy. This equation, right? If you lose the entropy, remember, if the entropy is negative, what happens to this sign? Negative and negative gives you what?
Positive.
Positive. Delta G becomes more positive. Delta G becomes more positive. The activation energy is higher. Make sense? All right. So you can see that the basic chemical experiments demonstrate how the enzymes work, right? So how is this molecule different from that?
It has no rotation.
No rotations already. Yes, so the starting material, we already eliminated rotations in the starting material. So in the transition state, all that needs to happen is for this oxygen to reach over, attack the carbonyl, for this alkoxide to leave. You don't need to freeze anything, don't need to rigidify anything because it's already rigidified. And you can see just by doing that, you increase the reaction rate by another order of magnitude, right? From 100,000 to 100 million here. All right. So this is an important way of how enzymes accelerate chemical reactions. And keep in mind that the enzymes, obviously the enzymes have to bind the substrate, but binding the substrate is not always a great thing. In other words, binding the substrate tightly is not always a great thing. Let's go back to this graph here. Now imagine if so it binds the substrate. Now imagine if this enzyme substrate energy is very low. In other words, if the complex is very tight, right, the free energy is very low, then what happens to this activation energy? It increases, right? So you want the enzyme to be selective. You want the enzyme to select the substrate out of thousands or millions of other molecules, right? But on the other hand, you don't want the complex to be very tight. In other words, if the enzyme binds the enzyme substrate complex tightly, that increases the activation energy for the reaction. The reaction will not proceed. You'll just bind the substrate and you'll stall. You will not go any further. And so what Linus Pauling proposed in 1946, basically he said that it's not that the enzymes have to bind the substrate very tightly. The enzymes have to bind these transition states. And remember, transition state is a hypothesis, right? Nobody has ever been able to capture or take a photographic image of a transition state, right? It has the lifetime of a transition state is shorter than one chemical vibration, right? It's a hypothesis. Nobody has ever been able to actually to isolate or to using any kind of instrumentation to learn anything about the structure of the transition state. And so, what he proposed that the enzyme active sites are complementary to the transition state of the reaction, and that they have to bind transition states better than substrates. So in other words, they have to lower the transition state energy. If they bind them better, then the delta G of the transition state is lower. And so what you have to look for, you have to look for these additional interactions with the transition state as compared with the ground state. And so I think, so we have some.
Dr. Kornienko,
Yeah.
I have a question real quick about the equation.
Which one?
The previous one on the graph.
This?
Yeah, that one. Yeah. Wouldn't an increase in entropy be positive? So wouldn't that be making the delta G more negative?
So basically the entropy is the entropy of the change in entropy is the entropy of the product minus entropy of the substrate. So if the entropy of the product is larger, or the entropy of the transition state is larger, then delta S will be positive. Is that what you're asking?
Yeah, it's because you said if you increase entropy, it's a negative S. So negative and a negative is a positive. But I thought increase in entropy was a positive S.
No, decrease entropy. Decrease in entropy gives you negative S.
Okay, perfect.
Based on this equation.
Okay.
All right. So here is the illustration of the binding of the transition state. So here's let's say we have a metal stick, right? Metal stick, our substrate, and we want to break it in half. So we're going to use some kind of magnet, enzymatic magnet. We call it, I think, stickase. Stickase is not on the slide yet, but it'll be on the next slide. So before this breaks, we have to bend it. We have to bend it, and the transition state will look like this. When it's bent, and this is starting to break. You see this surface is starting to crack, right? So this will be transition state, and eventually we break this into two halves and generate the product. So this would be with no enzyme. This is the free energy, just like we saw before, substrate to product. Now, so for this stickase, right? So let's say if the enzyme did not have, okay, what's this? Right, let's say the enzyme bound the substrate very strongly, right? Bound the substrate very strongly, but did not bind the transition state very strongly. Remember, for transition state, we have to accommodate this bent shape. And obviously in this active site, the bend shape will not be accommodated, but the substrate is very nicely accommodated. So here is the enzyme, right? Here's the magnets which will attract this metal stick into the binding site. So this is the enzyme substrate complex. And we generate some products. And so the substrate comes into interaction with the enzyme and precipitously drops down because of these positive interactions between the metal stick and the magnets at the active site, right? But then to break, you have to climb all the way up there. And why do you have to climb all the way up there? Is because there's no really good transitions. The enzyme cannot accommodate the transition state, right? The active site is not designed to accommodate this bent shape. And so you have to climb all the way up there. And so here's delta G of the catalyzed reaction, extremely high, extremely high. And so what needs to be done is you need to have an enzyme which can accommodate both. First, it can bind the substrate, right? Maybe not as strongly as on the previous slide. So if you go on the previous slide, this binding is beautiful, right? Binding is beautiful, but it doesn't accomplish anything. But if the enzyme can still bind the substrate, right? So there's still magnet here, binding to the, but then the magnet extends into the interior of the enzyme, making the stick bend, like so. Now the stick is bent, and then it accomplishes the, so the stick will break into two. And so here is the reaction coordinate graph. So here we have the binding of the enzyme to the substrate. You can see that the energy of the enzyme substrate is not as favorable as on the previous slide, right? Here you can see it's all the way down there because we have a beautiful binding site, but we don't need such a beautiful binding site. It can be up there. What's important is that this energy here, I don't know why this, what's important is that this activation state energy is small, right? And if it's small, then the reaction can occur at a fast rate. Does it make sense? So it is all about transition state stabilization. So keep in mind with the enzymes, binding to the substrate is good, but that's not the end of the story. If it binds too strongly, that's actually going to work against you. What needs to happen is the enzymes have to bind to the transition state more strongly, more tightly than they do to the substrate itself. And then if it binds to the energy of if it binds to the transition state, then this delta G of the transition state is low and the reaction can occur at a fast rate. Any questions?
Yeah, could you repeat that last part real quick? About the importance of it not binding too strong, but just enough.
Right, so the enzymes have to bind to the transition state more tightly than they do bind to the substrate, right? Otherwise, you will have to face this scenario here, where basically the energy of the enzyme substrate drops and you have to climb all the way up there for the reaction to occur.
Just to clarify, is by stabilizing the transition state, you are decreasing delta G, making it a more favorable reaction?
Yeah, you're decreasing the delta G of the transition state here.
Gotcha, thank you.
This one. This one. All right, so very briefly, catalytic mechanisms. Now this is, we still have a few minutes. So the enzymes mostly work by acid-base catalysis, covalent catalysis, or metal ion catalysis. So briefly, Now in the text, it's also actually a very brief description of the three. You can look at that. But acid-base catalysis is the most common. Now, don't worry about specifically what's written in these boxes. I think it's more detailed than I expect you to know. What is, but I do want you to understand what's happening in this graph, okay? So let's say if this is the peptide bond, amide bond, and let's say this is the enzyme, right? So let's say you have amino acid serine with hydroxy group. So serine will attack the carbonyl of the amide, right? Then the oxygen gets positive charge, this oxygen gets negative charge. And then the proton transfer happens from this oxygen to this nitrogen, from the oxygen to the nitrogen. And then when the electrons come back, when this tetrahedral intermediate collapses, you break the amide bond and you generate the ester bond. So this is just a tetrahedral intermediate mechanism from OChem2, right? So if you struggle with this, please open your OChem2 book, OChem2 lecture notes, and look at the mechanisms for the carboxylic acid derivatives. And you can see here, the key step here is the proton transfer, right? So you can see this is reversible. This is reversible, this oxygen is positively charged, but you want to make this nitrogen positively charged. So it doesn't go back, instead it moves forward. You protonate this nitrogen, and this nitrogen will leave, and the ester will form. And so there is now this can be accomplished without the enzyme, just in water, right? But the enzyme does a better job. The enzyme does a better job. So the water is on the left, the enzyme is on the right. And what these are the amino acids that can participate in these kind of proton transfers, right? So we have carboxylates, we have aspartate glutamates, we have lysine, arginine. Cysteine can also move the protons around. Histidine can move the protons around, serine and tyrosine. Right, so basically all these amino acids that have protons attached to them, which can be removed and can be replaced, can participate in these kind of hydrogen bond movement, hydrogen or proton transfers. Okay, so proton transfer is basically, it gives you a possibility for an acid-base catalysis, right? So this will be an acid. So the acid can protonate things, and this will be base. Base can deprotonate things. And so here's an example. On the previous slide, you saw an example where you had an acid and base working in tandem to accomplish a reaction. Now, covalent catalysis. So here, let's say you have a reaction where you have a molecule A and B, and it breaks down into A and B. Let's say it's some kind of hydrolysis, right? Let's say it's a ester hydrolysis. So by itself, hydrolysis is slow, but you can catalyze this reaction. Let's say if this X is part of an enzyme, right? Enzyme, some kind of amino acid. It can actually, let's say, think about of an SN2 reaction. Let's say X attacks A and B leaves. Then what do you have? You have A and X formed, right? And B is gone. And then hydrolysis will break down the AX and will regenerate the enzyme. Regenerate the enzyme and give you A and B separately, right? So instead of one step, which is slow, you have 3 steps, which are fast. Sorry, 2 steps in the actual chemical reaction, 2 steps. The enzyme attacks, the B leaves, and the hydrolysis releases the A from the enzyme. Now, the important thing here to keep in mind, what is this AX? So this is the covalent intermediate. It's known as covalent intermediate. Right? Which is then hydrolyzed by water. Okay, and can be serine, can be thiol of the cysteine, amine, carboxylate. What else do we have left? Metal ion and a metal ion, obviously, you know how that works, right? Basically, metals are Lewis acids, and we know how Lewis acids accelerate reactions, right? Just like in organic chemistry. Lewis acids interacts with substrates, stabilizes negative charges, right? So Lewis acids stabilize negative charges. And they also can participate in oxidation reactions. So we'll talk about that a little later. We'll see actually how, for example, iron, very important redox metal in biological systems, can participate in oxidation and reduction reactions. All right, I think we've covered pretty much what I wanted to cover with you today. So these are how enzymes work, some of the basic principles of their action. And on Wednesday, we're gonna talk about some specific enzymes such as chymotrypsin and lysozyme. And we're gonna start talking about kinetics. Any questions from today's lecture? All right, so I'll upload this to YouTube. I'll discussion, I think it's already open. So please start going over the lecture, start working on the sapling, read the text, and I would like to hear from you. Sounds good? All right, have a good week and stay safe.
Thank you.
Bye.